Hello, everyone. Welcome to Foresight's Neurotech Group. A little bit of housekeeping before we start. One, if you join this event via Luma, we're super happy to have you here. Just a note that these research seminars, they happen every month. So if you are interested in that, please shoot me an email at lydia@foresight.org, and I would be happy to get you up to speed. Number two, we're hosting our annual Vision Weekend from December 5th to 7th this year. And if you haven't heard about this, if you don't know about it, we'll be exploring ideas at the frontier of science and tech with over 300 researchers, entrepreneurs, and funders in attendance. So I'll include the link in the chat and you can check it out if that sounds good to you. Also, we're hosting a neuro workshop in October in San Francisco from October 11th to 12th. It's full, but we do need volunteers. So if that sounds something that could be up your alley, same thing goes, lydia@foresight.org. Without further ado, we're so excited to have none other than Dr. Michael Levin, Tarin Ziyaee, and Josh Bongard with us today. We're taking a little bit of a different format today. Instead of a presentation, we'll be having a fireside chat. And we will be talking about the question, embodied natural intelligence versus embodied artificial intelligence. What's the difference and what are we missing? So with that being said, we're super excited for today. Thank you guys so much for joining us.
Yeah, thank you, Lydia, for that. And welcome, everyone. Thanks for coming to this talk. I'll just start, folks, by, of course, reading the abstract. There's a famous quote by Jacob Bronowski. He said, "The hand is the cutting edge of the mind." And natural systems have this core ability to treat tools as extensions of the body, right? A trait that highlights an evolutionary advantage of generalizing motor skills. And the funny thing about this is that natural systems are really good at operating other tools and devices with no ethological precedent. For example, I can operate a spoon, a fork, a piano, a drone, a car, bulldozer. Monkeys can drive cars, right? Which indicates a general purpose machinery for learning how to extend control. And the question becomes, in this age of big internet data, why is it that modern robotics struggles with operations like this? Why is it, for example, that crows can operate a stick, but robotic systems sort of struggle to extend their control, even control their own bodies? So I'll open up with that. Of course, this is related to Moravec's paradox, and I'll open up with that large question to Dr. Levin and Dr. Bongard, and let's take it from there. So folks, if you want to chime in.
Mike, why don't you start us off?
Okay, well, I'll just talk about the biology side of it. Josh can say what's going on with the robotics, but on the biology side, I want to say a couple of things just to kind of set up how we think about this. First of all, the whole question of embodiment. So I think we as humans are very obsessed with three-dimensional space and with vision and watching things move around and like medium-sized objects moving through at medium speeds, moving through 3D space. And so we see crows and maybe an octopus and things like that. And we see intelligence. What I think we're terrible at noticing that same kind of sensing, decision-making, actuation loop, and so intelligence, problem solving in other spaces. And biology is using all kinds of crazy high-dimensional spaces that we find very hard to imagine. So when I say, for example, this physiological state space, metabolic state space, the space of gene expressions, anatomical morphospace. So when I say to people that actually morphogenesis, right, so the creation of the body is behavior. It's behavior of a collective intelligence, just like you and I are a collective intelligence. It is behavior of a collective intelligence navigating the space of anatomical possibilities according to behaviors and policies that can be analyzed by behavior science and so on. People find that very weird. And we have separate departments for developmental biology and neuroscience and behavioral science. I think these are all artificial distinctions. So when we talk about embodiment, we have to think about all kinds of strange spaces in which you can be embodied. And things like changing gene expression is actuation. And Moravec's paradox, like you got 20,000 genes potentially that you could be firing off at any given moment. These are all effectors that a cell will have, and it has to know how to run them, right? So that's the first thing. And then the second thing is, I think what's going on with the biology too is that it's sort of the epitome of the notion of beginner's mind. Like living systems cannot assume what exactly is going to happen. Never mind the outer environment, even their own parts are unreliable. Biology deals with an unreliable medium all the time. And so the reason that tadpoles with an eye on their tail can see out of the box, like no need for further rounds of selection, mutation, whatever, you radically change the sensory motor architecture, no problem, those animals can see. The same genome makes a human or it makes an anthrobot, no problem, right? Different ways of being. And I think that's because it can't assume much of anything going in. It has no idea what's going to happen. But what it is good at is doing the best it can with what it has. So the biology, I think that the flexibility of it comes from spending eons with an unreliable medium where you have to push on the problem solving aspects, not on memorizing solutions to specific policies.
Yeah. Fantastic, Mike. Yeah, Josh.
So following on in that line of thought, first of all, I'm Josh Bongard. I'm a professor of computer science here at the University of Vermont, and I've been working in the space of robotics for about 20 years now, and over the last 6 or 7 years working on biological robots with Mike, which we might get around to talking about. So taking, again, a historical view of all of this, we're well into the age of AI, and we're now just entering the age of robotics. So all of the lessons learned about biology, many of which Mike mentions, in my opinion, is paramount to keep in mind as we go about thinking about how to approach this robotics enterprise in general. AI and robotics is littered with assumptions about how animals and humans are and trying to build that into machines and things going fantastically wrong. We've made some progress recently. We've started to figure things out, but I say this to my students here all the time, thinking about thinking is misreading. The brain is the puppeteer. It's controlling the body, which controls tools in the external environment. Sounds perfectly reasonable, blindingly obvious. It's 100% wrong. So I'm putting my cards on the table for this chat. I want to militate against those assumptions. I think this is the useful work we need to do. There are huge amounts of very bright young people. There's huge amounts of financial resources, organizational resources going into robotics, and we've got to get this right. It really matters for a lot of reasons. So there's important intellectual work to do here to make sure that we're thinking through what is the proper framing to try and create, to design, manufacture, and deploy one-ton machines that are going to be operating at relatively high velocities, very near human beings. Like, this really matters. Just in my introductory comments here, I want to link them back to what Mike and Tarin was saying, is that biology is there. Mother Nature is giving us gradually examples, basically counter examples to our intuition for how things work, and we better listen. And we need to think about how to carefully chase after those more subtle lessons from biology to think through how to do robotics right.
Yeah, that's brilliant, Josh. And I think that's actually a very good segue into this notion that sort of picking back to Mike, what Mike said is that in biology, everything's messy. It's very messy. Your body will change forms. There are different things going on in the body every single point in time. How is it then, right? If we dig deeper into this, how is it then that natural systems in general are able to sort of, deal with this level of uncertainty with very short time horizons? And why is it that the paradigms we have today seem to not be sort of looking at this problem the same way, right? A lot of the sort of problems that we have today in robotics seem to, say, operate on the notion of, I will define a task, I will get some data to train some control policy on that. There could be a VLA behind that. Whereas in biology, we sort of picking up the cup is almost like the last thing we do. There's a lot of preliminary, if you like, I hesitate to use the word training, but there's a lot of preliminary training that went on behind that, where it seems like agents have understood their body well first, and then are able to extend that control to other things, right? What do you think the field is missing from a framing point of view that would allow us to sort of make strides in, bridge a gap between natural systems and artificial systems today?
Well, so from the biology point of view, I think the reason that biology is so good at extending itself is that, again, the question of where the boundary is between self and world is not given to any life form. You don't know, right? You have all kinds of things that you might do, and whether those things are part of you or they're not part of you, or they're going to obey your signals, or sometimes they will or not, whether you're an octopus and your limbs kind of have agendas of their own, but they're sort of somewhat controllable, or you're a newborn infant, and at first there's this like amazing thing that is very reliable. When you make noise, it brings you food. Like that's clearly part of my body. And then all of a sudden you realize some weeks go by and you're like, wait a minute, now I don't know, my hands are working better, but this other thing that used to be really reliable is not as reliable, right? And so this issue of which effectors belong to you and where your borders are is not set. It's plastic in biology. Living systems, again, because of the unreliable medium, they don't have the benefit of abstraction layers and too many error correction codes and all this stuff, which I actually think is part of the problem in our engineering, is that we focus on the fidelity of data, yeah, and also assume that there's somebody else is going to interpret it for you. All you want is for your device to keep whatever data it has. The register shouldn't float off and do weird things, and then somebody will interpret what those mean. Biology, there is nobody to interpret it for you. The registers will absolutely float off. You never know how many copies of anything you really have or what's going to happen or where the borders are. And so that plasticity, the need to constantly redefine what you are and what your effectors really are, and to tell the best story you can about your own memories, because you don't know what your memories mean at any given moment. You don't have access to the past. You have access to the memory engrams that past history has left in your brain and body. But it's interpreting those things to tell a story is like a constant effort. And so this is what biology commits to, is like constant interpretation of its own memories. And I think that's very different from how we engineer typically.
Yeah. Yeah, it's very true. It kind of reminds me, of course, of like prosthetics and just having like a joystick in front of me, for example, right? There is a new extension to myself in some way, or if people have a prosthetic because they unfortunately lost a limb or something like that, right? The body's able to, again, make do with this uncertain effector to learn how to use it, to learn how to learn, so to speak. And we see that across the board. In fact, there's an interesting paper, I forget the name now, but it talks about this notion of reverse pliers, where people are giving this tool and it was very non-intuitive how to use it. But after a couple iterations, they figured out that, oh, actually, if I push down, the things actually open, and if I pull up, it just goes to your point, Mike, about biology having to make do, or natural systems having to, at the base, assume that they can't really sort of predict the future that much. They sort of have to learn as they go and make do with uncertainty as they go. And I think that I think is a very salient point.
I like this idea of the plasticity of self. I think this is one important starting point for rethinking robotics. Robotics comes from a mechanical engineering, industrial, historical context where it was the opposite: maximize certainty, ensure that everything operates exactly the same way one time after the other. We can trace a historical thread all the way back to mass production and the advent of factories and organized labor. There's so much of that thinking that's now baked into how we approach autonomous vehicles and robotics that dangerously we don't even realize it's there. If you tell a roboticist, especially working in the commercial space, that we should make robots that have liquid cells that are uncertain and are not sure what they can do, what kind of actions and sensory repercussion loops they can rely on, that's anathema. So it's very difficult to make this case why we should adopt the plasticity of self. So there's a lot of important work that needs to go on in robotics, or at least somewhere between robotics and synthetic biology, to say, look, if you actually want a useful, safe, autonomous machine, it's got to be unreliable and learn how to deal with that, surf the edge of uncertainty. There's power there. And in the long run, that's the way to get to the dream of true robotics, the AGI equivalent of robotics. Then it becomes kind of a fun exercise, because then you start to think through, well, what would a robot with a liquid or undefined boundary of self look like? One of the ways that I've been thinking about this since starting to collaborate with Mike is that biology are machines within machines within machines. It's machines all the way down, which is not the case in robotics and autonomous vehicles. If you take an autonomous vehicle, it's a machine. If you zoom in on the wheel, you very quickly get to rubber. You get to an inert, non-machine part. We are already architecting and building robots that are not machines within machines within machines. They have a very clearly delineated boundary of self, and that limits them in some ways and also makes them dangerous in other ways. If the autonomous vehicle is overwhelmed, it's pushed into an out of distribution event, there are no other cells inside. There's no plan B. There's nowhere else it can turn to if this rigidly defined self doesn't know what to do in this situation. So again, tying back some of these deep intellectual points to like important real world practical matters, there's a link there to be forged and made clear for a larger public.
Yeah, yeah. Yeah, I think it sort of reminds me also, Josh, about the things that natural organisms are doing really when they try to navigate the world, not just spatially, but just sort of trying to understand the world, is that we're constantly running these little experiments with the world. You're sort of constantly like pinging it and trying different things and seeing what happens and reincorporating it, spawning new sensory motor programs and then killing them and then trying something else. And there's a very nice quote here about humans learn to remap motor commands to achieve goals with a novel tool, for example, right? Whereas it seems like a lot of what we do in robotics today tends to map to very particular motions, whereas what we really want to do is have a more goal-centric approach. I'm trying to attain some goal. Let me try different things. Let me learn from the environment what worked and what didn't and readjust. And that seems to be sort of like the modus operandi of natural systems by and large. Whereas we're not sort of training robotics today to experiment with the world as they see it. We're sort of shoving all this sort of data into them about the world as is. So I'm sort of reminded of this contrast, basically, from these two paradigms.
Well, and I mean, part of the trade-off there is that in biology, you don't know what you're going to get. So if you want to make a fish, you might end up with a sea snake or a bird or something else. Or you couldn't make a human, so you made an anthrobot. You couldn't make a frog embryo, so you made a xenobot, right? Like the biology will do all kinds of stuff. It won't necessarily do whatever you wanted it to do. And it certainly doesn't necessarily do whatever the past environment has prepared it for. It's kind of like what Josh said, applying these things to robotics. Yeah, you gain a lot of plasticity and flexibility and whatever, but you're not making old school machines then. You're making agents with intrinsic motivation, and you don't really know what you're going to get. If you do it right, you don't know what you're going to get.
Yeah, true. So also just mindful that Mike only has about 10 more minutes with us, folks. Let me switch over real quick to discussing imitation learning. I think it's actually a very nice segue into this, right? So imitation learning today, it's a very dominant paradigm within robotics of saying that, okay, we will have humans, for example, do a thing, and we will measure them doing action, and then we will field it, and then we'll sort of hope for the best. And sometimes they work when the environment, for example, doesn't change that much. How do you think about the paradigm, folks, of imitation learning as framed, where we will look what humans do, we will copy their actions, right? Not their reasoning processes, their actions. And then we will field it, and then we will sort of see what we get. From an intellectual point of view, how do we see this type of paradigm? Do we believe that there's an asymptotic limit to its capabilities, or do we believe that, that there's actually something there? And I won't bias everyone with my answer to that, but maybe ask Josh first.
Sorry, so about imitation learning, is that the question?
Yes.
So what to imitate and who is doing the imitating, right? So sorry to bring this back to the plastic self, right? It's, again, the assumption is often there's a robot and maybe it's learning to copy other robots and other humans. I co-authored a paper with Andy Meltzoff, a developmental psychologist, years ago now about who is my teacher. And it's been so long, I've forgotten everything about that paper except that question, right? Again, like if you don't clearly have a good boundary, it's not so clear who to learn from. The subject and object, the learner and the teacher, it's not so clear cut. And in machine learning and imitation learning, as you mentioned, it's clear. The robot is given, the learner is given the teacher. It's all set up for them. It's a very passive process. You've already solved the interesting part of the problem for the learner. And so yet again, there's an example about how if we go in with an incorrect framing, we might not get what imitation learning was originally designed to do.
Yeah, that's right. Yeah. And there's also this thing, I mean, there's a very nice summary about it. In imitation learning, for example, we're copying human actions. It's motion-centered, basically. And really the paradigm is saying that I will just simply copy these actions to get to this goal. The whole paradigm starts with an answer. Whereas it feels like in natural systems, you almost start with a question, which is saying that, what do I need to do to get to this goal? And am I getting closer? And so you develop your own actions, you develop your own movements within the context of these goals that also might be self-generated. Whereas in imitation learning, it's sort of like everything is given to this agent and we're expecting it to copy, which they do very well. But then when it comes to fielding them, we run into trouble because they cannot do this experimentation on the fly.
Yeah, I mean, I can mention two things here. One, just very briefly, because this stuff isn't out yet, but it will be in the next month or two. So keep an eye out. We're looking at something very strange. You could almost call it zero-shot transfer learning. It's things that data sets that have no business having any relationship to whatever problem you're trying to solve, that actually, it turns out, have really good actionable intelligence for it. And so this question of who are you learning from actually can get really weird, because we know that you can learn from your past self as in learning, you can learn from past generations of you as in evolution. Turns out you can also learn from some other thing that we don't quite understand yet. So stay tuned for that. But really, there are some really unusual sources for things you can learn from. And then the biology version of it looks something like this too. We have to remember this: caterpillar to butterfly. Okay, so caterpillar, soft-bodied robot, moves in a two-dimensional world, likes to chew leaves. You can train it to crawl over and eat leaves when you stimulate it with a particular light stimuli. Okay, so you train the caterpillar. Then it gets in the cocoon. It basically dissolves most of its brain. It breaks all the connections, rebuilds a brand new brain suitable for a hard-bodied robot, completely different, a control policy for that, right? And then you find out that it still has the original information. Now, the amazing thing here is not how do you keep data when your medium is being refactored. I mean, that's cool, but that's not even the most amazing part. The most amazing part is when you realize that the actual memory, the exact memories of the caterpillar are of no use to the butterfly. Butterfly doesn't crawl. It doesn't like leaves. It wants nectar. Like, none of the details are relevant. But what has happened is that those memories have been remapped onto a completely new architecture. So now you fly, now you're in 3 dimensions, now you can apply force to your wings because they're hard elements, and now you'll go look for different food and whatever. And so this is something else that we need to think about, that when you're learning or being trained, and that's a whole other question, is how do you know which is happening? You don't just soak up what was happening. You can apparently, at least in biology, you can remap it into your own architecture. And this is happening. We don't have to be a caterpillar or a butterfly to see this. This is you and I right now. When I'm talking to you, I am not thinking about, oh my God, which of his synaptic proteins do I need to tweak so that he understands exactly what I'm saying? I have no idea, because your brain is not like exactly like mine. And so we're using this, again, it's this like bow tie thing with language as a thin interface in the middle. You're going to do all the hard work of remapping whatever sounds I'm making into whatever changes of your architecture matter to you, with attention and memory and that's all that. And so even though we are the same species and roughly anatomically the same, already we have this problem that the micro details are not going to be remembered. But then in biology, you can have these crazy examples like butterfly, caterpillar, where it's like just like really. So that's the other thing about learning, is that it's never, at least in biology, it's never a tape recorder. It's always messages that you interpret and see what you can do with.
Right. And just in the last few minutes that we have you, Mike, I'll just also ask you this. Its tools become a part of us, right? We consistently extend the extent of our control with our bodies and other things. I hold a spoon, I hold a fork, whatnot. I like this notion of this extension of control also applying towards the social realm. For example, I think you talk about this in the context of, what was it called? Cognitive light cones, I believe, right? Where agents, as they become more and more sophisticated, extend their cognitive light cones. And in doing so, we can bring other tools, effectors, maybe even other agents into our fold, and then of course try to sort of control this context. That I just think is a very interesting way of looking at this, and also it's not something that I think we even think about in modern day robotics, from the context of like, it's almost like the body is a first training data or source of training data almost, and then we should start there. That is what it means to be embodied in this sense, and then extend that. So I just wanted to anchor to the cognitive light cone concept that you have.
Yeah, I think that's exactly right, because the responsibility of being a high-level entity is telling compelling stories that align your parts to do things they wouldn't otherwise do. So when you are an embryo, as opposed to 100,000 or 1,000,000 individual cells, like when we look at an embryonic blastoderm, why do we say there's one embryo there? What is there one of? Well, what there's really one of is there's one story, right? One path in anatomical space, and all of the cells are being committed to, they're all going to cooperate because they all believe they can go in that. And you can interfere with that, and you can do all kinds of interesting things there. But what makes it one embryo as opposed to a bunch of individuals is that alignment and the collective. The whole point is that there's this constant circular causality with this virtual governor that sets the agenda for the pieces, which is not easy because the pieces are competent. They have their own agenda. They give them a microsecond, they will go off and they will do their own thing if you don't keep exerting some sort of plausible control over them that they like. If you do it in a way they don't like, they will eventually defect and leave. And this is cancer and metastasis. This is when the cells decide that this multicellular bargain's not working out for them because it's too much stress or whatever. So learning to maintain control over your parts is the first thing you learn and the hardest job you have, I think, as a high level system.
That's awesome. It's awesome. Yeah. So we will end your segment, Mike, with the body's the first source of training data. How about that? And that might be a good sort of motto for us there. Yeah. Okay, Mike. Well, thank you very much for coming.
Thank you, everybody.
Josh, you'll be up to the two of us to solve Morvik's paradox for the next half an hour. As I look forward.
Deal.
Thanks, guys. Appreciate it a lot. Thank you.
Absolutely. Take care, Mike.
Bye.
So, Josh, do you want to round this out, Josh, before some other maybe points we can make, and then I think we can open it up to Q&A.
Sure. Yeah, I'd be happy to. I think obviously this was just the tip of the iceberg, and I think that's important to remember is to remain humble when we go about thinking about what's happening in biology and porting it into technology. We've been talking a lot about bodies and embodied cognition. One of the other things I just wanted to throw in before we open it up to Q&A is learning that there are places we haven't even looked in biology for hints. So one of the things Mike and I have been working on recently that we're excited about is this concept of polycomputation. So there is vibration at work in the human body and the human brain, especially at small scales. When you're dealing with vibration, you have power at many different frequencies. And that means that if you treat those frequencies as parts of computation, there are things going on across the frequency spectrum in neurons and other parts of the body that we've only just started to look for. And that's just to look at. And that's one example where we've taken that idea and now Mike and I have been trying to build polycomputational technologies, metamaterials that vibrate at many different frequencies. And those materials that vibrate at different frequencies, they're performing computations at different frequencies, but at the same place and at the same time. So it looks like a quantum computer with no recourse to quantum effects. So we're jazzed about it. But again, it's just an example of thinking very different, being humble in front of biology, not trying to enforce a frame about what we're looking for. Let's not focus on synaptic plasticity and imitation learning. There's lots of other things going on. And how can that give us brand new ideas, brand new directions to pursue in trying to create the next generation of intelligent technologies?
Yeah, that's right. Josh. Yeah. And it just reminds me also of the fact that there's, I think also for historical reasons, been a lot of focus on, there's almost like this marriage between computer vision and robotics. And I think for understandable reasons historically, because we had the computer vision sort of revolution back in 2012, AlexNet and so on and so forth. And that sort of got folded into robotics. But like to your point, I also think that real agents in the physical world today, they have to deal with forces, right? Like literal mechanical forces on their bodies with objects against objects, right? And there's almost like this entire zoo of information in the real world around forces that we are just not able to capture today at scale. This was like sort of pegged to something very practical. And I've always found that very interesting and sort of very notable because we don't have like the image net of forces as agents try to manipulate things, right? That doesn't exist. And if we even had a modicum of that, one would imagine that we could reappropriate a lot of these items from biology of extended control and so on and so forth to make these agents actually work properly. It actually reminds me of that we may even be starved, not just in, for example, multi-agent simulations or things of that nature, but the world is very mechanical and we don't have data sets to support that at scale today. And
exactly. We're starved.
Yeah.
We're starved. And I think in many ways, we don't even know what we're starved of. We don't even know what roboticists talk about big action. AI was all about big data. Robotics is where's big action? There is big action. If you work for some big tech companies, you've got fleets of autonomous vehicles covering planet, and they're all uploading to the cloud. So there is some big action, but is that the right thing? That's maybe the potatoes. Where's the meat? Potato. Like, are we sure we're getting all the data that's necessary for being an intelligent, embodied actor in the world? Who knows? My guess would be probably not. We don't even know what kinds of data we need.
Right. Yeah. Yeah. Awesome. Well, thank you very much, Josh. Yeah. And Lydia, I think this will be a good point for us to open up to the Q&A. I think they're in the chat, if I'm not mistaken.
I think, Micah, you asked about a question. So would love for you to kick us off.
Sure. One of the things we like about automation and robotics is that it is reproducible, reliable, copyable, unlike biology. If we build robots that are more like biology, I worry we start to lose a lot of those things. I'm curious, what do you imagine is left once we have these robotics that are very biological-like in how they behave, how they act? Are they still going to be able to copy them? Are we still going to be reliable? Or are we just going to basically be building another human?
Yeah, I think it's a really good question, Micah. I'm obviously hopelessly biased. I don't know what the answer is, but my response to your question is, yes, we still want reliable robots, but reliable in what way? We want them to embody a particular action, but they don't necessarily need to be reliable in terms of geometry, doing it on their own, the time horizon over which they do it. One of the things that I've learned about biology from Mike is they are reliable. Biology can keep doing things. They can keep enforcing a consistent narrative, for example, like Mike was just talking about. But the way they do it shifts from moment to moment at all time scales, at every spatial scale, right? It's the ship of Theseus. It's always, the ship is the thing that you want to be reliable, not the planks. And I think in robotics, we're focused on the planks. It should be this robot doesn't get broken and always picks up the box with both hands so that it doesn't drop the box. That's wrong. That's not the way to think about it. It's too much of a focus on its proximate causes, the actual body itself, the fixed body, rather than focusing on ultimate causation, what we actually want to have happen. And it's fluid robotics, at least in theory, should still be able to provide that kind of reliability. How exactly, to be determined.
Great. Thank you. Lisa?
Hi, Lisa.
Gotta turn that on.
Muted.
It's good to see you
Hey,
again.
Lisa.
Yeah.
Hey, Z, I had a question actually about something you just said about there's all this kind of information in the world. We don't even know what we're kind of learning from necessarily, things like that. Actually, so coming from the perspective of like, we are fundamentally humans who are either scientists, philosophers, all these things, people who want to design robots and want to design systems that help us design robots, things like that. We have a very limited perception of the information and the signals in the world that we are able to access. There might be things that we and our machines can't even necessarily detect. So how reasonable do we think it is that we're actually going to be able to sort of understand this and solve these problems?
Sorry, was that directed at me, Lisa, or was it for Josh? Or?
It was for Josh.
Okay.
Oh,
Sorry.
for me. Oh my gosh.
Oh, I'm so sorry, Josh. I can repeat.
Oh
my
my
God.
God. No, no problem. Yeah, I don't know. I think something that Mike said is that there's a hard bargain here. We're going to have to give up certainty, the industrial approach to certainty and tolerances. We're not going to get it all. We're not going to get robots where we can say, you go do something useful on behalf of humans and you figure out how, and we create the system that creates the machines that do that. We're going to get something that's at a weird point on this Pareto front of an open-ended system and a system that does what we would like it to do in retrospect after we've seen what it does, right? It's going to be Pareto optimal. There is no cherry on the sundae. We're going to have to make decisions about where on that line we want to lie. And that's fundamentally not satisfying for everyone.
Yeah, that makes sense to me. Cool. Thank you.
I think just to add, there was the previous question, I forget the gentleman's name right now, but about reliability. I'll also just say that we want to reliably have reliable systems, I guess, in a sense, right? And one of the ways in which you can attempt to do that, I would say, is can the system sort of learn on the fly with the environment as it finds it, right? Because we will never be able to fully control the environment in its entirety. For maybe like very specific automation tasks, I think that's a different story. And I think we sort of made great strides there. And I think that problem is more or less solved in my opinion. Like if you really control the environment, and you really control all the variables, like in factories or something like that, yeah, you can have an automaton do things. And of course, you can do that physically. The issue becomes when you deal with the open-ended world as it is, and you don't have all the information, and you will never be able to get all the information because the world is constantly changing. And this is especially true when you start to interface with humans, when you start to interface with the outside physical world. At that point, I think that the key here is for agents to learn how to figure out on the fly, to learn how to experiment, to learn how to ping the environment, and to get the information necessary for them to do something else, which sort of takes us into things like sensory motor synthesis and spawning of programs and stopping it and pulling back. And that's not something that we train for in robotics today. But I think that's how you'd get more reliability, concretely.
Thank you. Christian, would you like to ask yours?
Yeah, hi, thanks. What's a bit source to get ideas about projects I can work myself to start learning more about these topics? I'm asking from a beginner's perspective.
So I'll let the professor take that question.
Obviously, hopelessly biased. My PhD advisor, Rolf Piper, and I wrote a book a long time ago before the AI summer. So a lot of what's in that book is already out of date, but the title is How the Body Shapes the Way We Think. It's almost a historical document at this point. I think there's still, hopefully, a few nuggets of ideas in there about how to think differently. I'd say more recently, if you're a coder, my lab runs a subreddit, which I just typed into the chat, called Ludobots. There's a whole bunch of programming projects there that ease you into the shallow end of all the nuts and bolts of robotics, neural networks, a little bit of neuroscience, a little bit of biomechanics, a little bit of physics engines, the kinds of tools that tend to be used to tackle these sorts of questions. And yeah, you can just follow those programming projects. And they're designed so that when you get to the end of one of those paths in Ludobots, you've got a platform, an experimental platform, and then you can hopefully have some intuition about how to take that platform and use it to test out some of your own ideas. So yeah, those would be my 2 pointers. I'm sure others on this call also have ideas. Feel free to chime in on chat.
Definitely, though, folks, I'd definitely recommend Josh's book on this, How the Body Shapes the Mind. I've read it multiple times, and it's a piece of work. It's amazing. So I definitely recommend everyone start there for sure.
Thank you. Awesome.
Amazing. Anyone else? Morgan.
Yeah, thank you. Yeah, just to also say how grateful I am to Dr. Bongard for all his online courses and lectures, which are also a great resource. Just wondering about where you see biological simulations coming into evolutionary robotics and yeah, what new aspects of biology can we start to incorporate that aren't in those models yet?
Yeah, I think that's a really good question. Oh boy, where to start? So the xenobots, the easiest thing is just don't simulate the biology, just use it as it, not as is, almost as is out of the box. One of the many thrilling experiences of working with Mike on xenobots is how surprisingly easy it was to, like Mike would say, change the narrative, to convince Frog that it doesn't necessarily need to be Frog. It can be other things, like a robot, like, wow, there you go. So again, there's been this very old framing in robotics that dates back to the cyberneticians in the 60s and 50s and even earlier, that you look at biology, you abstract it, get rid of all the messy, unreliable parts, and then put some metal around it and you're done, right? But there's many other ways we could do this. We can either just borrow biology and make robots out of living tissue and skip the abstraction part altogether. There's biohybrids. Now, there's a whole field in robotics called biohybrid robotics, where you want to build a reliable, safe, useful machine. You consider all the components you need to go into that machine, and you weigh them up. Maybe for component X, a technological solution makes sense, but for component Y, a biological component makes sense, right? So there again, it's not necessarily simulating, it's making a chimera. It's combining technology and biology so that you're combining the best of both worlds. It's just a whole other way to approach it. Then we can exploit the AI revolution and just dump all the biology data sets we have into an autoencoder, get back a latent representation that captures what the biology is doing, and strips away the unnecessary details. It's the cybernetician's dream comes back again. So we can do a lot of that. And then you can take the autoencoder and stimulate it so it generates, it builds an organism out of metal parts, right? This is this thing that AI is very good at doing, painting in different styles. You can ask an AI to paint a robot and use different styles, use human cells, use frog tissue, use metals, use ceramics, use rare earth metals that are not so rare yet. So it can be very nimble. You can get AI to be very nimble with the building blocks of robotics. These are just new options of ways to mix and match biology and technology. And which of those is going to bear fruit, who knows? But to me, that's part of this robotics revolution that we're entering into. There's whole new ways to mash up biology and technology. Thanks for your question.
Assuming we want to continue building robots out of silicon and steel, do you imagine in the future that we would build the way we're building now, where you have a central brain that controls the parts? Or do you imagine that we'd build a robot hand that has its own brain, an arm that has its own brain, and a central processor or whatever, it has to convince the arm to do the thing it wants, and the arm has to convince the hand to do the thing it wants? Like, which of those paradigms do you kind of see the future of robotic being?
I think you put your finger right on it. It's starting to be called meta robotics or metabotics. So it's admixtures of control policy and physical hardware all the way down. And then obviously all the way up, because all of this data is feeding back into the cloud. So the cloud basically is deploying a whole bunch of different bodies and learning what works. So you can, like you said, you can drill down and try and cleave the Cartesian cut, make sure that there's a good admixture of body and mind at every level, at every spatial scale within an individual machine. And then the same thing that goes all the way up to the cloud, where the cloud might decide to physically weld or combine multiple machines. It can also play with combining mind and machine at larger and larger scales, which again is something that biology does. Ants build ant bridges, humans come together in various ways. I think that's the future, right? Like you said, traditionally we've just decided there should be about a 6 foot tall self made out of metal, and then make all the metal, and then we'll drop a control policy into the GPU, right? Why that scale? Why that division? I mean, obviously we're biased. There's reasons why we've chosen that spatial scale. It's arbitrary.
Right. And actually, I just wanted to ask also the audience here, just maybe flip the paradigm a little bit. What does the audience believe is sort of the missing link or links that explain the gap between natural embodied intelligence and artificial embodied intelligence as it is today? So I'd be very curious about what the audience thinks. If you guys want to put this into the chat, or someone wants to raise their hand and sort of chime in, ideally with a concise summary. What do we feel is this gap?
I think for me, it's the first question I asked, which was, we want our robotics to be much more reliable than biology is, and therefore we are building things that are more reliable than us, and the trade-off there is that they are not as capable as adapting as we are. I mean, if you want to build something that's super adaptable, you have a kid. That's easy. We know how to do that. We specifically want robots to do something that's not like the thing that we can already do really well. And so this has led us down a path that has led us to kind of where we're at.
Yeah, thank you, Micah. Anyone else?
Perhaps more cognitive development needs to be understood or incorporated. Representational redescriptions that cognitive development researchers talk about in children. That's worth it.
It's actually interesting you mentioned children, because there is, I believe that a lot of focus, well, babies, it turns out, I forget the exact age range. I think it's very early on. They're very adept at paying attention to two things: gazes and hands, right? And I think that kind of tells you a lot about, how the system is primed to sort of think about social intelligence, right? Where is the attention of this other agent? And then also what is their intention to control things, in a sense, right? So I think I've always found that very interesting, because you have the physical interaction part of it, right? And then you have the social interaction part of it. And for me, those are the two things that I think they're just not given enough oxygen in the conversations within current robotics. Awesome, folks. Well, If there are, I think we're at the top of the hour. If there are no other questions, I think we can adjourn. Folks, I'll just ask any other questions out there? Ether, going once, going twice. All right, going 3 times. Well, thanks everyone for attending this. Thank you, Lydia, of course, for inviting us into the Foresight Forum. Thanks to Mike Levin, of course, for attending. Unfortunately, I had to run after half an hour. Josh, always a pleasure to see you as well. I think this is just like the tip of the iceberg when it comes to the closing the gap between natural systems and artificial systems. But I think the age of interaction is upon us now. And I think that the more conversations we have like this, the more likely it is that we'll bridge the gap. Thanks again, Josh. Thank you, Lydia. Thank you, Mike. And thank you to the audience for making this possible.